Okay, so let's start. Do you folks have any questions on the one-pass algorithms that we covered so far, especially the nested loops join, the block-based nested loops join, any of those aspects before I go ahead? Any questions? Okay, so let's get going with two-pass algorithms. Okay, so we've considered one-pass algorithms. Mainly the consideration there was I need to ensure that at least one of my two relations is small enough to fit in memory, or small enough such that I can create some form of a data structure in memory so that I can then scan through the other relation and then perform operations as necessary. So the two-pass algorithms are to deal with the limitation that maybe we don't have enough memory to store one relation in its entirety. So how do we deal with that case? And so you might need to take multiple passes across each relation in that setting. Okay, so let's start with duplicate elimination. So duplicate elimination, once again, the extended relational algebra operator is delta. And how would we use duplicate elimination, or how would we apply two-pass algorithms for duplicate elimination? It's pretty simple. We simply do sorting, but we don't include any duplicates. So the first step is to sort collections of blocks of size m. You write this out to disk, and then you merge them in the next pass. So let's say you have, or maybe I'll try it differently. Let's say you have, this is your data on disk, and these are the blocks that your relation is present in. And let's say my m, which is the number of blocks that I can hold in memory at a time, is 4. So I might bring these 4 blocks in to memory, sort it, and then write it back out to disk. Okay, then I'll bring in the next 4 blocks, sort it, write it out to disk. Next 4, write it out to disk, and so on. Okay, I'm going to erase this one for now. Okay, so now you have 3 groups of sorted runs in on disk, right? So these are 3 runs. So these are sequences of blocks that are individually sorted, right? So now that I have outputted these runs to disk, each of which is of size m, the next step is to merge them in a merge sort like fashion. For that, what I need to ensure is that at least one representative, sorry, not this guy, and this guy, at least one representative of each sorted run is present in memory so that I can merge them. So I would have this block, and this block occupy 3 slots in my memory to begin, and I have yet another block for the output. So I will merge the records in these 3 blocks, removing duplicates. Any new records that I will find, I will plop it into the output. As soon as the output gets filled, I will flush it to disk, and I will keep doing this. If I get done with this block, I will move to the next block here, and if I get done with this block, I will move to the next block here in my sorted run, and so on. Okay, so this is just like a merge sort. It's nothing particularly challenging. I just want to ensure that for each sorted run, each collection of blocks that are sorted in my first pass, I have one representative each in main memory so that I can perform the merge operation. Okay, if I didn't have one representative in main memory for each of these sorted runs, then I can't perform the merge operation. Okay, so that is the issue. If I can't do that, then I might end up having to do yet another pass. So I might do one merge pass, output another sorted run, and then take the sorted runs once again, do another merge, and keep doing this. Okay, so that's the fallback strategy. But for now, we're going to focus on the two-pass strategy. So what are the conditions under which this two-pass approach will work. So question to you folks. So firstly, let's talk about the two steps. The first step is you sort groups of blocks of length m into sorted runs. You output that to disk. The second step is you merge m minus 1 runs, and then you include each tuple that you found in and place it in the output buffer. And then you keep doing this as you process these runs, and it's like a merge sort. Once you're done sort of processing all of the blocks, you flush the last output block to disk. So the question for you folks is, what is the constraint on the number of blocks that you need? So how many blocks would you need in main memory to be able to run this algorithm as specified? Remember, the main constraint is I need to have one representative of each sorted run in memory when I'm doing the merge. That is the main constraint. So what is the condition on m that will help me meet that constraint? Any guesses? Okay, so let me ask a simpler question. So in step 1, I'm sorting the relation into runs of size m, right? So how many runs would there be? This is a fairly simple question. So I have, yes? BR by m, right? So you have B of R by m runs at the end of step 1. Now the second condition basically says I want to ensure that I have at least one representative from each of these runs. And I need to reserve one block for output. So I have m minus 1 slots to hold at least one representative from each of these runs. So my condition is basically B of R by m. This is the number of runs. This is less than or equal to m minus 1. Okay? Are you folks with me on this? Okay, so this is nothing but B of R is less than or equal to m times m minus 1. So that's a constraint of B of R on m, okay, or B of R. So that's our constraint on memory. Now let's talk about cost. The cost here is, for step 1, I'm reading in all of the blocks of the relation, writing out all of the blocks of the relation. So that's 2 times B of R. And step 2 is I'm reading all of the blocks of the relation once. The final write out is not counted, so it's just B of R, so it's 3 times B of R. Okay, so that's a cost. So as a comparison with the one-pass approach, we had cost was B of R. You only need to read the relations. Read the relation once, but the condition on memory was a lot more stringent. It was B of R is less than or equal to m minus 1. Okay, so this is a loser condition, and therefore is easier to meet. Okay, so B of R only needs to be less than or equal to m times m minus 1. In this case, B of R needed to be less than m minus 1. Okay? Yep?
I'm sorry, is it possible you could get rid of that message again?
Oh, fun. Okay, sorry. What did I do last time? Yes. Thank you for letting me know. Okay, so compared with the one-pass approach, the cost is B of R, and the assumption is more stringent for the one-pass approach. B of R has to be less than m minus 1 as opposed to m times m minus 1. So if BFR is larger, then we will need to use the 2-pass approach. Okay, so let's look at what happens if I want to apply this sorting-based approach to other operations, right? So which of these operations do you think can benefit from sorting? So we've already done duplicate elimination. So which are the other operations that can potentially benefit from sorting? Any thoughts on this? Yep.
Maybe selection.
Why would selection benefit from sorting?
Because if you're looking at like several tuples and you know that you have an idea of where it could be located based on whatever value you're supposed to look for, then you could just iterate over those particular amount of tuples.
Correct. So what you're saying is that selection would, sorting would help selection if I had a means to figure out where in my data those tuples, the sorted tuples actually lie. Turns out if I don't have an index, for instance, there's no way I can figure out where the data, where tuples with a certain value actually lie. So it doesn't really benefit me in that sense. Also, for a 1-pass approach, selection is extremely cheap, right? It doesn't have any constraints on memory. You just need one block to make a pass through the relation when you're applying selection. So in the case, okay, so there are 2 cases. One is if you have an index and if you don't have an index. If you have an index or if you have some other mechanism to store, to retrieve the blocks in sorted order, then you're absolutely right. Having, being able to filter out some portion of your relation without having to look at it is a boon, right? But if you don't have an index, you can't retrieve the records in sorted order, then sorting doesn't actually help you for selection and projection, as it turns out, because for selection and projection, you just need one block in memory to make a pass through the relation. Okay, so it's not benefiting you in terms of relaxing the condition on memory, because anyways, for selection and projection, the constraints on memory is fairly easy to meet. You just need one block, right? You just need to make a pass through the relation, like cross out all the tuples that don't match the condition, and then output them. So for selection and projection, sorting doesn't help you loosen the memory requirements. Okay, so sorting doesn't help you loosen the memory requirements for selection and projection, because for selection and projection, it's actually already pretty easy to meet. For the other operations, these are all similar to duplicate elimination because all of them rely, at least in the 1-pass case, all of them rely on having at least one relation, or in this case, for the grouping case, for all of the groups to fit in memory, right? So they rely on all of them rely on having a pretty large structure fitting into memory. This may not be possible under memory restrictions, right? So if your relation is large enough that it doesn't fit in memory, then you can't actually run these algorithms using the 1-pass algorithm. Right, so you need to resort to the 2-pass variant. So for set operations, join and grouping, sorting can actually help relax the memory requirements. Again, we are operating under the scenario where there are no indices yet. We'll talk about indexes towards the end of the class. Okay, any questions about this? Any objections? Okay, so let's see how these operations can benefit from sorting. Okay, so let's start with grouping. So grouping is the extended relational algebra operator is gamma, and let's say I want to do city and sum of price. So I want to group by city. I want to compute the sum of price. So how would I do this? Well, I'll follow the same recipe as duplicate elimination. I would first sort the tuples. And then compute the sum of price for each group. So what would I sort based on? City, right? So I want all the tuples corresponding to a given city to be together so that I can collapse them to give one value. So in order for that to really benefit me, I should sort by city, right? So I would sort by city, and then I would use that to compute the sum of the prices. So one way to think about that is you have your relation, and let's say in this case I have, I'll eliminate these last two blocks. I have m is equal to 3. I will sort, I will take these three, and let's say m is equal to 3. I'll bring these three blocks into memory. I will sort it based on city. So maybe I will have cities beginning with A first, and then cities beginning with B, and so on. So it's in sorted order, these tuples. Similarly, the next set of tuples will be read into memory and written out in sorted order. So cities beginning with A, cities beginning with B, and so on. Okay? So in next, what I will need to do is I'll need to bring one representative of each of these two runs into memory, and I will keep an output buffer. The output buffer is going to compute the city comma sum of price for all of the city tuples, right? So here maybe I have one with city A and price 10, and here I have one with city A and price 20. Maybe the next tuple here is city B, price 10. Next tuple here is city A, price 30, and then maybe C, 40. Okay, so let's say those are the tuples. Once I have read A10, A20, and A30, I can, as I'm reading A10, A20, and A30, I can update the sum of price in my output buffer from 10 to 30 to 40, to 60, right? So that's the total sum of the prices that I've seen so far. And now I know that my A tuple is complete. I won't be seeing any more A tuples because this is in sorted order and I'm processing it in sorted order. So now when I see the B tuple, I can create a new tuple in the output with B comma 10. So that's my starting value. If I see any other B tuples, I will update that. In this case, maybe I won't see any other B tuples. So I might start a C tuple with 40. I will update that as I see more C tuples, and so on. Okay, so once this output buffer gets filled, I will say, okay, good riddance, go to disk, and then I'll flush that to disk and start a new one. If any of these two blocks get completed, I'll drag the next block in sorted order and process that. Okay, so not very different from duplicate elimination, or not very different from basic sorting. We are just the key step is a sorting step, and then once you have things sorted in the order of groups, merging that is pretty straightforward. Here, instead of eliminating duplicates while merging, you're simply doing the sum of the tuples while merging. Okay, so that's the only difference. Okay, so that's this. That's grouping. What is the cost? The cost is going to be the same as the previous approach, right? So the same as sorting, same as duplicate elimination. You are reading the relation in once, writing it out once, reading it in again, and therefore it's 3 times B of R. What is the constraint on memory? Again, it's similar to the previous one. You have B of R is less than or equal to m times m minus 1. That's what we saw on the previous slide. So it's less than m squared. In the past, we had B of R is less than m, which is a more stringent condition to perform grouping, and therefore the constraints on memory have relaxed with sorting. Any questions about this? Okay. So let's talk about binary operations. Okay, so far we've talked about unary operations. Let's talk about binary operations. So let's say union, intersection, difference. Okay, so the key idea here is instead of sorting one relation, I'm going to sort multiple relations. So I'm going to sort both R and S on a certain attribute, and then I'm going to process them in sorted order in a merge kind of an operation. So The first question is, what would we sort on? What would it make sense for us to sort on in this case? So in the duplicate elimination case, we sorted on the entire tuple. For the grouping case, we sorted on the grouping attributes. This case, what would we sort on? Again, not a trick question. What do we think? What would it be helpful to sort on in order to perform intersection, union, or difference? Yep.
The keys?
You can sort on the keys. That'll be better than sorting on the entire tuple, but what I was going for was entire tuple. So if you sort on the entire tuple, that'll work. So I'm a little worried that no one answered. So are you guys following? Is there something that's confusing? This is not a hard question. This is a simple question, right? So why would I want to sort on anything else but the entire tuple, right? So if I can sort on the entire tuple, then I will be able to identify tuples that are common across R and S. If I'm doing an intersection, I can try to figure out that these are indeed common, and therefore I might want to output them. If I find that they are not common, then I might not want to output them. So sorting on the tuple is the right way to go. So are you folks following? Is there something that's confusing up until this point? I'm happy to go back and tell you about something that is confusing if there is something. But so any questions on this stuff? So what part is confusing?
When you say sorting on a tuple, what do you mean? Like you can't sort on every attribute.
So you sort on the entire thing, right? So you sort on. You can think of it as you you consider. Let's say one option would be to concatenate the set of attributes together and sort them, or you can consider some form of lexicographic sorting on the entire set of attributes. You are indeed sorting on the entire set of attributes. You're not sorting on individual attributes by themselves, but you're sorting on the entire collection.
I'm confused. If you have, say, name and numbers and something else,
Yeah.
then they would each have different sortings, right, depending on.
Correct. Correct. So you can, so one option, and there are many ways to sort this, and it doesn't really matter which approach you use. All that it matters is that they are sorted in a consistent order. One approach would be to sort first by name, and within the ones that have the same name, you sort first by the second attribute. Within the ones that have the same second attribute, sort by the third attribute, and so on. So that gives you a consistent sort order. You can, like I said, you can smush all of the attributes together and sort them in that way. That'll also work. You can sort them in another weird fashion where you sort first by name. What would be? There are lots of weird ways you can sort. All of them will work, basically, right? So the only thing that matters is that you're sorting on all of the attributes. You're not just sorting on one of them. If you sorted only by name, that's not going to work because the tuples that have the same set of values for all of the attributes are not going to be next to each other. Okay? Any other questions about this stuff? Okay, so I'm going to go ahead, but please feel free to stop me. I know it's early in the morning, and so most of you are still half asleep, and that's totally fine. I am half asleep too. But if you have questions, stop me. Okay, so I'm assuming that the reason why you're not stopping me is that you are half asleep, but you're still understanding everything. But if you are having issues, stop me. I'm more than happy to slow down and explain things in more detail. Okay? Agreed? At least please nod right now. Okay, good. Okay, so So what do we sort on, right? So we sort on the entire tuple. So once again, it's divided into two steps. So the first step is I'm going to sort R or split R into sorted runs of size M, and then split S into sorted runs of size M. Okay, so I'm going to take R and then and generate sorted runs from them, right? So you have R. So let's say these are the blocks of R, and these are the blocks of S. So I'm going to grab collections of M blocks from R, sort it, write it out to disk, grab the next collection of M blocks, write it out to disk, grab the next collection of M blocks, sort it, write it out to disk. I'm going to do the same thing with S. Grab the first collection of M blocks, sort it, write it out to disk, next collection of M blocks, sort it, write it out to disk, and so on. Once I've done that, the next step is to do a merge, right? To do a merge, I need to ensure that from every single sorted run that I generated in my first step, I'm going to have one representative from each of them. Okay, so I need to have from all of the runs from R, I need one representative, and from all of the runs from S, I need one representative. And then once I have one representative from each of them, I can then do the merge. Okay, so a natural question is, why do we need all of the sorted runs in memory at once? Well, the reason for that is that if I'm missing one of them, then I end up giving you an incorrect answer, right? So if I don't have a representative from a sorted run in memory, then I might end up giving you an incorrect answer. So for instance, if I'm doing an intersection, let's say I missed out on one of S's sorted runs. Okay, so one of S's sorted runs, I don't have a representative in memory. In that case, I may end up incorrectly not outputting something that should have been output, right? So maybe that sorted run is the only run from S that had a certain tuple T. If that is the only run from S that had a certain tuple T, and there is a tuple T in one of the runs from R, unless that run is in memory, I will never output that. Okay? So that's the issue. So if I don't have a representative from each of the sorted runs in memory, I'm going to make mistakes. So which I don't want. I don't want to make mistakes, so I want to have at least one representative from every sorted run in memory. Now the question is, how many runs are there? And so there are X runs from R and Y runs from S, which is, so how many runs, so how much is X and how much is Y? So notice here that I am splitting R into sorted runs of size M and S into sorted runs of size M. So X is nothing but B of R by M, and Y is nothing but B of S by M, right? And I need both X and Y, at least one representative from each of these runs, to be in memory. So I need X plus Y is less than or equal to M minus 1. This is nothing but B of R plus B of S divided by M is less than or equal to M minus 1, which is B of R plus B of S is less than or equal to M times M minus 1. Okay? So this is my constraint on memory. What is my constraint on, what is my cost? Well, in step 1, I am reading and writing out both of R and S, and in step 2, I'm reading in R and reading in S. Therefore, my cost is B of R plus B of S times 3. Right? Any questions about this stuff? Okay. So the cost is BFR plus BFS times 3. The constraint on memory is the sum of the blocks of R and S is less than M times M minus 1. So that's our constraint. And this is much more lenient than having to store one of the two relations in memory, right? So in the one-pass algorithms, we require to have one of the two relations in memory. In this case, we don't require to have one of the two relations in memory. All that we need is BFR plus BFS is less than a quadratic term in M. Okay? Okay, so let's talk about what the merge rule will be. So in this case, let's say I'm doing set intersection. What would I use as a rule for merging? So I have now one representative from each of the sorted runs of R, one representative from each of the sorted runs of S. Now I need to merge them in sorted order. What would my rule be for merging if I'm doing set intersection? What would my rule be if I'm doing set intersection? What is the criteria for merging? How would I merge if I'm doing set intersection? So you can think of each sorted run that I have from S. Each of them is sorted based on the entire tuple. So you can assume that each of these sorted runs are sorted based on the tuple. So you have one sorted run or one representative, the top block from each of the sorted runs of R, the top block from each of the sorted runs from S in memory. Now I need to merge them to construct the intersection. What would I do? How would I do that? Yep.
If you find any duplicate tuples, you just keep one of them and you throw out the others?
If you find any duplicate tuples, you keep one of them and throw out the others. So that's, at a very high level, that is absolutely the right answer. So, so more precisely, let's say you look at the smallest tuple in sorted order across all of these blocks. Okay? Let's look at let's take the smallest tuple across all of these blocks. If, let's say, without loss of generality, let's say it's in R and not in S. So let's say it's in R, in one of the sorted runs of R. If it is in R but not in S, then you can evict it. You don't need to worry about that tuple because it's not going to be part of the intersection. Right? If it is in S but not in R, then again you don't need to worry about it because it's not going to be part of the intersection. You can eliminate that and then you can process the next tuple. If you find that there's a tuple that matches across them, then you can output that to the intersection, right? You can output that to the output block. The one small caveat is that there may be many copies of this tuple that span separate blocks. Okay, so there may be many copies of this tuple that span separate blocks. So that might lead you to some edge cases that you might need to be wary of. So in some cases you may need, so let's say you have 10 copies of tuple A, and then in your first block, and then 10 copies of your tuple A in the second block. You don't want to output A 2 times or 10 times to your output since you're doing set intersection. So you need to worry about the fact that there may be duplicate tuples. So that's one edge case that you need to be careful of when coding this algorithm. But otherwise, your approach, which is keep one copy of every tuple that is common between any run of R and any run of S, output that, and keep going is the right strategy. That is, at a high level, that is the right strategy. Okay? So, said another way, if you have two tuples where one is less than the other, for now I'm assuming just one sorted run from each of R and S. If you have two tuples at the top of those two blocks where one is less than the other, then you can delete the smaller one so basically if A is less than B, then you can delete A. If B is less than A, you can delete B. Otherwise, you output both A and B to the output, but keep track of the fact that you've output A to the output so that if you see another copy of A, later you don't output it again. Okay, so that's the only sort of edge case. It's kind of an annoying edge case, but that's the only thing that one would need to worry about. But at a high level, it is simply maintain one copy of everything that's in common. Yep.
When you say keep track of output there, we can just assume that we don't need an extra memory block to do that.
We don't need an extra memory block to do that because you can always look at the output block to see what you've last output.
Okay. What if that last output block we've just filled it up and we've written it to memory and then we have nothing there? I mean, that would just be an edge case to think about, I guess.
Yeah, that would be an edge case, and it's a good point, but it's not. So it is still. Databases can still assign temporary variables. They still have a temporary heap where they can assign variables and keep track of information between runs, because they do need to decide on what query execution strategy is going on and how far they've proceeded on that. So all of those variables need to be maintained somewhere. So even though I'm saying there's only M blocks, those are the M blocks that store the data. The temporary computation stuff might still be stored somewhere else. Yeah, but that's much smaller than these M blocks. But you're right. Okay, so let's talk about joins. Okay, so we are done with one example of a set-based operation. You can think of the other set-based operations and come up with similar rules for merging for them. So let's talk about joins. Before I get to the 2-pass algorithm for joins, let's talk quickly about the 1-pass and the 1.5-pass algorithms. So the 1-pass algorithm was very simple. You load the smaller table to memory and then load the other table block by block. The cost of this was B of R plus B of S, and the constraint was that the minimum of B of R and B of S is roughly less than M. Okay, so basically at least one of them had to fit in memory. Now, if this constraint was not true, we had the block nested loops algorithm. The block nested loops algorithm would load to memory M minus 2 blocks of S, so as much of S that you can fit into memory, and then you loop over the blocks of R. So you bring in a group of blocks from S, you go through once all of the blocks of R, bring in the next group of blocks from S, go through once all of the blocks of R, and so on. This was quadratic, right? So this was B times B of R times B of S divided by M. And so this was, in some sense, you can think of this as a nested loop with one loop corresponding to R and then an internal loop corresponding to S, or the other way around. In this case, it's external loop corresponding to S, internal loop corresponding to R. Okay, so this is the nested loop algorithm. This works under most settings, right? So M is greater than or equal to 3 was the only constraint that we had to meet in this case. So these are the two extremes. So this is linear, the cost is linear, it's just bare minimum reading R once, reading S once. This is pretty extreme. This is quadratic, if you will, in R and S. This is pretty stringent on memory. You have to have one of the two relations in memory. This is not at all stringent on memory. The only restriction is that M is greater than or equal to 3. Okay, so these are two extremes. Let's talk about something in the middle. So, so the first approach is a naive approach, and let's start by talking about that. So the first approach would be to sort these two relations in entirety and then do a merge. Okay, so how much would I need to spend in order to sort them in entirety? So remember that sorting a relation was 3 times the number of blocks of the relation, because you need to read it once, write out the sorted runs, read the sorted runs in, and then you're done, right? So you don't count the cost of the output. In this case, we do need to count the cost of the output because it is an intermediate step. right? So you still need to count the cost of the output because it's an intermediate step. So instead of having 3 times B of R for the cost of sorting, which is what we've seen so far, it's now going to be 4 times B of R because you're counting the cost of the final write to disk. And then you can read both of these relations in sorted order and match the tuples between them. So once again, you have B of R and B of S because you're reading these relations in. So in total, it's 5 times B of R plus B of S. What is the assumption here? The assumption is B of R is less than or equal to M times M minus 1 and B of S is less than or equal to M times M minus 1. Where did I get this constraint from? So where did I get these constraints from? Why do these constraints hold? So firstly, is the algorithm clear? So the algorithm basically says, I'm going to take first take R and then sort it, then take S and sort it, and then read them in sorted order and do a merge, and I'm done. Right? So where do these constraints come from? Yep. From sorting, right? So it's basically just that I need to have one representative from each of the runs in memory when I'm doing my merge as part of step 1, as part of the sorting. For that, I need to have B of R divided by M is less than or equal to M minus 1, and therefore B of R is less than or equal to M times M minus 1. That's it, right? Nothing surprising. Okay, any questions about this? Yep.
The first constant, therefore, B of R plus 4B of S, where did the 4's come from?
Okay, so the cost of sorting that we've seen in the past was 3 times B of R, right? So you read the data in once, you wrote out the sorted runs, you read the sorted runs in, and then that was it. So that was 3 times B of R. Now in that costing, we did not count the last cost of writing out the final result, because that would be common no matter how you implement the operator. In this case, since it's an intermediate step to the overall procedure, we can't avoid that cost. So you still need to count the cost of writing out the sorted results. So in this case, it's 4 times B of R as opposed to 3 times B of R, since it's an internal step. Now, then after that, once again, you're reading these things in sorted order, but the eventual write out is another cost, but we are not counting that because that's going to be common. Right? So that's why there's a 4 as opposed to a 3. Okay? Okay, so, but turns out I can do something smarter, so let's try to figure out what I can do. Any thoughts on what I might be able to do in order to do this better? So do I really need to sort the relations in entirety? Before I do a merge? Is there a step that I can skip? Let's take inspiration from like the grouping based case, right? So in the grouping based case, we sorted based on the grouping attributes, and then we did a merge, right? Such that the grouping attributes are common. What can I do in this case? Can I skip? Do I really need to pay 5 times B of R plus B of S? Do I really need to do 2 passes first, write it out, and then read them in to merge? Or can I skip some steps? Any thoughts? Okay, so what I can do is, firstly, instead of sorting the entire relations, I can sort based on the join attributes. Okay, so I'm going to sort based on the join attributes. And once I'm sorting based on the join attributes, so I'll get back to this difficulty later. Once I'm sorting based on the join attribute, I don't necessarily need to sort the relations in entirety. I can just directly operate on the sorted runs and do a merge. Okay, so I start by writing out runs of R and S sorted on the join attribute. So for that, I need to bring in R in groups of M, write it out, bring in S in groups of M, write it out. So there's a cost of 2BR and 2BS. Now I have sorted runs of R and S on disk sorted on the join attributes. The next step is to simply merge these runs in sorted order and match the tuples. Okay, so for this the cost is B of R plus B of S. Now what is a constraint that I need to meet? So the constraint that I need to meet is, again, not very surprising. I need to have one representative from each of the sorted runs in memory in order for me to do the merge. To have that, I need to have B of R plus B of S divided by M. This is the total number of runs that I have. This is less than or equal to M minus 1, and therefore B of R plus B of S is less than or equal to M times M minus 1 is less than M square. The cost here is simply 3 times B of R plus B of S, right? You don't really need to sort everything in entirety before you do the merge. You can just skip those two intermediate steps and just sort on the join attributes and then do a merge. Any questions about this? Does it make sense? Yep.
So I still don't understand how this way is different than the past.
Okay, so in the last way I was doing something stupid, which is to complete sorting. Okay, so I read the relation in, or read groups of M blocks in, sort them, write those groups of N blocks out. Okay, so I do it for every group of M blocks, and then I first sort the relation completely. So I get one representative from each of the sorted runs, and then I sort it completely. So I have a sorted order for R, complete sort order for R, and a complete sort order for S. Then finally I do yet another step of merge to merge the two sorted lists. So instead of doing the second step of merging the sorted runs only of R, only of S, and then doing a grouped merge of sort and a grouped merge of the sorted R and sorted S, I can collapse all of that down into one step. Does that make sense?
Yeah.
Okay, so here instead in this case, notice that, let me try to erase this. In this case, at the end of this step, I don't have, the only thing that I have is I have groups of blocks of length M that are individually sorted. I don't have any other property that holds across these relations. And then after that, I'm getting in, so let's say there are, let me give you, take numbers. So let's say I have, I don't know, what would be a good set of numbers? Let's say I have 100 blocks of R and 100 blocks of S, okay? And then I have, let's say, 10 blocks of memory. Would that be enough? Okay, I need to make sure that I'm meeting my condition. M times M minus 1. So Okay, so let me try to reduce that a little bit. So let me take m is equal to 10, b of r is 50, and b of s is 50. Okay? So so in this second algorithm, what I'm going to do is I'm going to take b of r. So I have 50 blocks of b of r, group it into groups of 10 each, and then sort them, bring them into disk, bring them into memory, sort them, write them out. Okay? So I have basically these groups of blocks from R. There are 5 groups of such blocks from R that are written out to disk that are in sorted order. Okay, so there are 5 such groups. Then from S I have okay, so from S I have basically 5 groups of 10 blocks each, correct? Once again, I've written them out to disk. The next step is to merge one block from each of these okay, unfortunately, once again, here I don't have enough blocks in memory. So you guys need to help me out with better numbers. What would be better numbers? So maybe I'll go with 4. Would 4 work? Okay, 40. So let's try 40 instead of 50. So do you see that I don't have enough blocks in memory to do the merge here? In order for me to do the merge, I need one representative from each of the sorted runs of R and each of the sorted runs of S. There are 10 such blocks, and I only have 10 memory blocks, and therefore that's not going to work. I need more blocks. Correct? Okay. So I'm now going to change my numbers to 40 instead of 50, and let's see whether that works. B of R is 40, B of S is 40, and M is still 10, let's say. Okay, so I have 4 sorted runs of R and 4 sorted runs of S. Okay, so now the second step here is basically doing a merge of these sorted runs. So I'm going to take one representative from each of these sorted runs and then do a merge, right? So that is the second step. So is this algorithm clear to you? Okay. So the other algorithm is just a stupid version of this algorithm, like I said. So I'm going to explain that version to you once more. All that I was doing was I was going to, so I have once again 40 blocks of R and 40 blocks of S. Correct? So I'm going to first take one group of 10 blocks each, sort it, write it out to disk. One group of 10 blocks each, sort it, write it out to disk, and so on. Okay, for both R and S. The second step is I'm going to sort R in its entirety. So I'm going to get one representative of this sorted run, 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 and then merge it. And at the end of that operation, I have sorted all of R. I have not touched S at all. Okay?
So in the second way, you may do a merge and matching into one step.
Exactly. So it's sort of merging and matching into one step. So here you're merging all of the R's into one, and then merging R and S next. In the other way, you're merging R and S together. Okay? So nothing fancy. This was a retarded algorithm and the next one isn't. That's the only difference. Okay. So let's move on. All right. Okay, so the one caveat that I wanted to mention is this one. So there may be cases where many tuples in R may match many tuples in S if at least one set of tuples fits in within the M blocks, then we may be okay. Otherwise, we may run into issues. So for instance, if there are, just go back and think about this. If there are lots of copies of tuples that have the same join attribute value, then I need all of those tuples to be present in memory at the same time in order for me to be actually able to do the join. If they are not present in memory at the same time, then I won't be able to do the join, right? Even though I'm processing them in sorted order, right? Does that make sense? So let's say I have from relation 1, I have attribute A is equal to 1, and so I'm relation 1, relation R is A comma B, relation S is A comma C. So I have 1 comma 100, 1 comma 200, 1 comma 300, and let's say this is 1, 1, 1, 1 comma X, 1 comma Y, 1 comma Z. Okay, so this is R and S. In order for me to be able to do the join correctly, I need 100 to be present in memory at the same time as X, Y, and Z, 200 to be present in the memory at the same time as X, Y, and Z, and 300 to be present in memory at the same time as X, Y, and Z. If they are not present, if by mistake I've gone and evicted one of these tuples, then I'm no longer going to get the correct result for join. Okay, so if by mistake I had already evicted one of these tuples from one of the two relations, I'm no longer going to get the same result for join, and that is an issue, right? So I have to be careful when there are many tuples that have the same join attribute value. If they have the same join attribute value, then the constraint effectively is that all of those tuples need to be in memory at once so that I can construct the join across them. If they are not, if I can't fit them in memory at once, then I'm in trouble. For instance, if my memory only allows me to keep 2 tuples from R and S at a given time, then there is no way I can do a join correctly because I will miss out stuff, right? So if, for instance, these 2 tuples are in memory from R, these 2 tuples are in memory from S, I'm not going to be able to join 100 with 1Z, or 200 with 1Z, or 1X with 300 and 1Y with 300, because they are not in memory at the same time. So essentially, if I have very skewed data such that there are lots of tuples that have the same join attribute value, then I have to unfortunately resort to nested loops join. That is my default. Nested loops will work well because it's essentially going to consider all pairs of tuples and then output stuff, so it's the right thing to do if you have a lot of skew in your data. In most cases, this may not hold, so we are usually in good shape, but if it does hold, our default is to use nested loops. Okay? Okay. All right. Running way behind schedule. Let's move on to hashing. Okay, so the idea behind, so far we talked about sorting as one technique for a 2-pass algorithm, and another technique is to use hashing. So the idea behind hashing is to partition relations into m roughly equally sized buckets on disk. Okay? And in order to do that, you need to have some form of hash function that will allow you to do this partitioning. Once you have these buckets, the next step is to examine these buckets in one shot, independent of other buckets. So for instance, if you hash based on attribute A, then you know that if you're looking for values corresponding to a certain value of attribute A, you only need to consider one bucket, you don't need to consider other buckets. Okay, so everything that needs to be considered together is in a small number of buckets. Okay, so that's the constraint that this partitioning based on hashing provides you. So therefore, you can do the operation by only looking at 1 or 2 buckets at a time. So either one bucket corresponding to your one relation R, or one bucket each for one from R and one from S. Okay, so how do these partitioning algorithms look like? So essentially, you have one input buffer, you apply some hash function, you have m minus 1 buckets that you can hash into. You, if a tuple that you're getting from input hashes into one of these, you add it to that bucket. If you finish processing this input buffer, you get the next block. And you keep going. If one of these output blocks gets filled, you output it to disk. Okay, so this is similar to, slightly different from but similar in spirit to sorting things into runs. Okay, so what is the size of each partition? In this case, you have m minus 1 partitions, and therefore the size of each partition is roughly b of r by m minus 1. Okay? Any questions about this? Okay. So, what's a constraint such that each bucket fits in memory? So in order for each bucket to fit in memory, this, which is the number of blocks within a bucket, this must be less than r. So br divided by m minus 1 should be less than or equal to m. Okay, that's a constraint for this collection of buckets, or this collection of blocks that are part of a bucket, this one or this one, to fit in memory. And we'll revisit that in a second. So let's talk about duplicate elimination as a first hashing based operation. So the first step is to partition R into m minus 1 buckets. So once again, you can think of this as one input bucket, and you're using a hash function, you're dividing it up into m minus 1 buckets. And as and when any of these output buffers gets filled, it gets evicted and you create a new output buffer in its place. So what would I use as a hashing function? Well, I would hash on the entire tuple, right? I would take the entire tuple and then I would apply a hash function on that to give me a partitioning or a hashing of this relation into m minus 1 buckets. And what would the next step be? The next step is simply to apply duplicate elimination to each bucket, right? So you simply apply duplicate elimination to each bucket. You can use the one pass duplicate elimination strategy here. The cost of that, if you remember, was b of r. This one pass duplicate elimination strategy assumes that each bucket fits in memory, plus you have one for the input buffer, and therefore b divided by m minus 1. So this is the size of the bucket, and this is the number of blocks allocated for recording delta of this bucket. Right? So b divided by m minus 1, which is the size of the bucket, the number of blocks in a bucket, is less than or equal to m minus 1. You also have an input buffer. So once again, it is like if we go back and look at the one pass algorithm, what would be the easiest way to do that? So if you remember the one pass algorithm for duplicate elimination, you had the constraint which is m is greater than or equal to b times delta r plus 1, or in the worst case b of r plus 1, and you had an input buffer and a dictionary for the duplicate elimination. So this is a one pass algorithm assuming the relation fits in memory. So now we have the one pass algorithm assuming the bucket fits in memory, right? So you have partitioned things into buckets, and you want to ensure that each bucket fits in memory. So it's the same as the previous algorithm, but applied to each bucket. So B of r divided by m minus 1 is less than or equal to m minus 1, and therefore B of r is roughly less than m squared. All right? Any questions about this? Okay, so the costs and constraints for this hashing based algorithm is roughly similar to the sorting based algorithm in that B of r is roughly less than m square is the memory constraint. The cost is roughly 3 times B of r is the cost constraint. This is roughly similar to the sorting based operator. Let's talk about grouping and aggregation. Okay, so once again, this is very similar to the duplicate elimination. You use the grouping attributes as a hash function. You partition R into m minus 1 buckets. So once again, you partition R into m minus 1 buckets. And each of these buckets is now processed by itself in the next pass. So you apply gamma to each bucket, and because you've used the grouping attributes as a hash function, all of the tuples in the same group will be in the same bucket. So that is a guarantee that you have, and therefore the second step is nothing but the one pass gamma. You just do one pass gamma. So once again, it is B of r divided by m minus 1. This is the number of buckets, number of blocks in each bucket. This needs to fit within the memory slots that I have, which is, so this needs to be less than or equal to m minus 1. So B of r is less than or equal to m minus 1 times m minus 1. So once again, this is roughly similar to the sort based operator for for grouping. Okay, so let's talk about joins. Okay, so we've talked about the in some sense a one pass hash based join. So the one pass hash based join was to simply scan one of the two relations into memory, build buckets and main memory, then scan R, hash the tuples of R and output those that match. And the assumption was that the smaller table is smaller than the memory available. Okay, so that was a one pass algorithm that we had already covered. Let's talk about the two pass hashing based joins. So the first two steps are predictable. This is just like what you would do for grouping and duplicate elimination. So you would just partition S into m minus 1 buckets using the join attributes as a hash key. Second step is partition R into m minus 1 buckets using the join attributes as the hash key. And then you send all of these buckets to disk. The next step is essentially like a merge. Okay, it's essentially like a merge. So in order to do, well, it's less than, so I should take that back. It's less like a merge and more like a one pass hash based join. So similar to similar to how the two pass duplicate elimination and the two pass grouping based algorithm had the one pass algorithm as a subroutine for each block. Similarly, the last step here is essentially the one pass hashing based join applied to each block or each bucket. Okay, so the third step is essentially joining every pair of buckets which have the same bucket number, and we are using the one pass algorithm for this. For us to use the one pass algorithm for this, at least one of the buckets from either R or S needs to fit in memory, and for that to happen, I need minimum of B of R comma B of S divided by m minus 1. This is the least number of blocks in one of the buckets of the two relations R or S. This should be less than or equal to m minus 2. Why m minus 2? Well, I need one block for the input buffer, one block for this or whatever I need for this structure. Let's call this structure here, and then one block for the output. So I need this structure to fit within m minus 2 because I need one for the input and one for the output. So the minimum of b of r comma b of s divided by m minus 1 needs to be less than or equal to m minus 2, and therefore the minimum of b of r and b of s needs to be less than m square. Okay, so in all of these two-pass hashing-based algorithms, the duplicate elimination, the grouping, and the join, in all of these two-pass algorithms, so the first step is partitioning the relation, and once you've partitioned the relation intelligently, the last step is always the one-pass algorithm for that operation, okay, applied to buckets at a time as opposed to the entire relation at the time. The buckets are a lot smaller than the entire relation, which allows us to use less memory than we would need if instead we were using a one-pass algorithm. Okay? Does this make sense? Is this clear? Any questions about this? Any questions at all? Okay, so this was a two-pass hashing-based join. The cost of this is 3 times b of r plus b of s. Why is that? Well, you're reading in the relation once, you're hashing it and writing it out, and then you're reading it in again. So it's 3 times b of r plus b of s. Okay, so there's some stuff that is important but is not covered in the lecture. Please go ahead and read that. I am already way behind schedule, so I won't be able to cover everything in class. This is a fairly hairy and complicated topic, so please do take the reading seriously. Okay, so comparing sorting and hashing for binary operations at least, for the sorting based implementations of binary operations, we had the size requirement as b of r plus b of s should be less than m square. For the hashing based implementation, the requirement is instead the minimum of b of r and b of s is less than m square. Right? So we saw that here that we don't require both b of r and b of s to be less than m square. We only need one of them to be less than m square. So that's one clear benefit of hashing as compared to sorting for the binary operations. Okay, so this is a clear place where hashing wins. The other benefit is that the output of sorting based algorithms are in sorted order, so that's another benefit. This may be useful for subsequent operations if we are doing a further grouping or some other operation. So in this case, sorting wins. And finally, the hashing based algorithms rely on the hash function doing a good job, rely on buckets being of roughly equal size. This may be a problem. There may be cases where the buckets are not of equal size, and in such a case, once again, sorting wins. Okay, so overall, it's not a clear distinction between sorting and hashing. Both of them are pretty good, but there may be cases where one wins over the other. It's not clearly determined upfront, at least. There are other differences as well. Please go ahead and read the textbook. I will cover index-based algorithms in my next class. Yep.
So when we say the sorting-based algorithms, are those using B-trees?
No, sorting-based algorithms, the ones that I mentioned were precisely the two-pass sorting-based ones that I just mentioned earlier. So not using B-trees per se. So it's sort of just the ones where I basically bring in blocks at a time, construct sorted runs, write them out, and then so on. The first set of algorithms that we covered before we got to hashing.
So these hash-based algorithms are different than like the hash-based indices. Is that what you're saying? Are they like?
Yes. So I think these are two different topics. So there are indices and there are implementations of these binary operations. The implementations of binary operations use hashing and sorting, but they're not using the indices yet. We'll get to the indices in a little bit. Okay. And so the sorting-based algorithms, essentially, the difference there is that what they were doing was to grab groups of m blocks at a time, sort them, write them out, grab groups of m blocks, sort them, write them out, and then process like in a merge sort type fashion, you were processing these sorted runs, right? This is taking groups of blocks and then partitioning it using the hash function, and then taking each partition and operating on that as a unit. So that's the conceptual difference between these two styles of algorithms. Yeah?
Okay. Thank you.
Okay. Cool. See you folks on Monday.